Okay guys, let's discuss electron configuration. So if you have looked at your notes and started trying to prepare for this, you notice that a lot of our electron configurations start with this setup, okay? So let's talk about what each of these letters and numbers mean. So the S and the P's, all of these are the shape. So like the S orbital is a sphere and the P orbital, remember we have a dumbbell, but also remember we can turn that dumbbell or infinity sign 3 different ways, okay? The number in front, this 1, 2, and 2, these are our principal quantum numbers, if I can spell. Okay, the principal quantum number is like n equals 1, n equals 2, and this is how far from the nucleus you are. So the difference between like 1s versus 2s, so if the nucleus is in the middle, 1s would be that first circle ring, okay? 2s would be the second circle ring, okay? And so let's put that together with 2p. 2p is like you have all these infinity signs, but they're just further away. They're on that second ring, okay? So I know my drawings are awful. It's hard to really picture, but this is what all of this means. So the last thing in this setup that we need are these numbers up top. So 2, 2, and 6. All of these numbers are the number of electrons in that sub-level or suborbital. Okay, so any p orbital, because you see it has 1, 2, 3 different orientations, any p orbital can hold 2 electrons, okay, because each line like this, each orbital line can hold 2 electrons, okay? So if I were talking about, let's clean some of this up. So if we had like 3D, well, the d orbital has 5 different ways that you can draw it. So I could draw, remember that's the clover. I can draw all those different ways, but there are 5 different ways, 5 different ways to draw it. And so over here I drew like up and down vertically, but we normally draw these in a line. So we normally say 3D and we draw 5 lines above it for all 5 options. Okay, so since this is an orbital, 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 and orbital, these are 5 orbitals. Each can hold 2 electrons, so we can put 2 electrons in each one. Sorry, I messed that up. So total, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 10 electrons total, okay? For the f orbital, so if I'm going to change it from a d orbital to the f orbital, I've changed this to like the 4f orbital. Well, the 4f orbital has 7, so 1, 2, 3, 4, 5, 6, 7 different orbitals. And again, each of them can hold 2 electrons. So if you put these in, let me show you the order that we draw them. We spread them out. So there's my first 7, and then the next 7 will come up and pair with the opposite spin. So total, the f orbital can hold 17 electrons. So on your paper, that's why this up here is showing you like the s orbital holds 2 electrons, the p orbital holds 6, the s orbital 2, p orbital 6, d 10. So it doesn't change. So this is like 3s, 3p, and 3d. They still only hold 2, 6, and 10. Okay, remember this 3 in front just tells me how far away from the nucleus I am. So the difference between 3s2 and 2s2, the difference between these is 1 is further away. So the 2s is on that second ring, the 3s is on that third ring. Okay, same thing with the p and the d orbitals. Okay, so let's talk about the order of the electrons, how you put them into their shells. So let me erase this. Hold on. Okay. So there is an order to this, and we can look at our Christmas tree diagram. Okay, so the Christmas tree diagram, it looks like this. I'm going to draw it. On the first subshell, we only have an S. On the second level, we have an S and a P. On the third level, we have an S, a P, and a D orbital. On the fourth, we have an S, we have a P, we have a D orbital, and now we have room for a fourth orbital. So what's changing from like 1 to 2, 2 to 3, 3 to 4 is that we're getting further away from the nucleus. So once you get further away, you have more room. So when you have more room, you can hold that D orbital. And then again, on the fourth orbital, you have enough room to hold the F orbital, okay? So that's why, like, on the first level, you only have room for a circle. You don't have room for anything else. On the second level, you have room for an S and you have a P. On this third ring, you have room for S, P, and D. And then on the fourth ring, you have room for all of them, okay? So let's keep going on our diagram. Okay, let me fix what I broke. Okay, on the fifth level, you have an S, you have a P, you have a D, and you have an F, okay? The reason it's called Christmas tree is because then we start going back down. So on the sixth level, you only have enough electrons to go to the D orbital. You may have more room to keep going and have like an F and a G and so forth, but we run out of electrons. So I'll show you what I mean in just a second. On the seventh orbital, we only have an S and a P. Okay, so again, I told you that every single one of these S orbitals can only hold 2 electrons. Okay, because the difference between 1s and 3s is that 1 and that 3. But this does not mean like 3 times S, okay? That is not what that means. It means an S orbital, meaning a circle, on the third ring out, okay? So the difference between 1s and 3s is how far away from the nucleus you are, okay? That's all there is. So an S orbital still only has one way that it can be turned. So if you don't know what I'm talking about with ways it can be turned, in your notes on your PowerPoint, it has like right here, let me see, right here, these shapes. Remember I said that the S orbital can, no matter which way you turn it, here's my 3D axes. No matter which way you turn it, it still looks like a circle, okay? See, these look the same. For the S orbital, that means that you only have one orbital, okay? Just one. And so again, each orbital can hold 2 electrons. So the S orbital can only hold 2 electrons total, all right? The P orbital, for the P orbital, remember, we can change it different ways. We can stand it up, we can lay it down, and then we can put it coming out towards you, okay? And so there are 3 different ways the P orbital can be drawn, 1, 2, 3. And each one can hold 2 electrons, okay? So the P orbital total can hold 6 electrons, and so forth. The D orbital right here, so I'm right here now. The D orbital, this clover, can be drawn 5 different ways. So there's 1, 2, 3, 4, 1, 2, 3, 4, 5 for the D orbital. So again, 2 electrons in each. there's 10 total in the d orbital. There can be, okay? In the f orbital, there's 7 different drawings, 1, 2, 3, 4, 5, 6, 7, this is f, for the f orbital, and so each one can hold 2, so there's 14 total possible places. Okay, so let's go back to what we were doing though. Okay, so I wrote on here that all of the s orbitals can hold 2 electrons. That does not change, okay? So the p orbitals, each of these can only hold 6. The d orbitals, each of these can only hold 10. And the f orbitals, each of them can hold 14. Okay, so these are all of our orbitals, but when we start writing the electron configuration out for a compound, or not a compound, I'm sorry, for an element, we have to count up how many electrons. So your element. First, find how many electrons, okay? That is going to be equal to the atomic number if there's no charge, okay? And then you are going to follow the arrows on this chart until you use every electron. Okay, so what I mean by that is an example. If I want to do, if I want to do the electron configuration for, let's do magnesium. Okay, I find magnesium, which is Mg, and I say the atomic number for magnesium is 12. So I have 12 electrons, okay? So the arrows for this chart never change. So let me find a bright color. The arrows will go through 1s, and then 2s, 2p3s, 3p4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. Okay, so those are the arrows, and those arrows never change. That's just a rule that we have. So to do the electron configuration for magnesium right here, we have to follow these arrows until we get 12 total electrons, okay? So we're going to go through the first arrow first and write down what you have. That's 1s, and it can hold 2. So it holds 2 electrons. So we had 12 electrons. We subtracted 2 because we put 2 in this first shell. That gives me 10 electrons left. So keep going. The next one is 2s, and it holds 2. So now 10 minus 2 gives me 8 left. Okay? Well, we go through the 2p, and that holds 6, so we can use all 6 of these. So 8 minus 6 gives me 2 electrons left. Okay, well, we just keep following the arrow, and we go through 3s, and it can hold 2, so our next is 3s2. So then you want to look at these superscripts and add up the numbers. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12 electrons. So we know that we are doing the right one for magnesium because we got 12 electrons out. So your answer, your electron configuration for magnesium would be 1s2, 2s2, 2p6, 3s2. Okay. What if we were trying to do, instead of magnesium, what if I asked you for sodium? Okay. Sodium has 11 electrons, so this adds up to 12. The one we just did adds up to 12. To get to 11, you just take 1 away right there. So it would be 3s1 is what we're ending with, and these stay the same. 1s2, 2s2, 2p6. Okay? If you wanted to start with the chart, you could do it again up here. You could, you could start over all the way at the top of the chart. And you could follow the arrows. Again, like I said, the arrows don't change, they just got erased. Okay, and so we would have to start at the top of the chart, and this time we're doing sodium, and that has 11 electrons, so we go through the first and we say 1s2. That is now used 2 electrons, so we have 9 electrons left. So keep going, 2s2, so now we've used 2 more, so we have 7 electrons left. So 2p, we can use all 6 spaces, and now we have 1 electron left. Well, now we go into 3s. It can hold 2, but we only have 1 electron left, so we only put 1 there. So if you look at this electron configuration, that's what I wrote down here. 1s2, 2s2, 2p6, 3s1. So the only thing else that we need to learn right now is the orbital notations. And orbital notation is just basically drawing all this out with your arrows for your electrons, okay? So this practice one is for chlorine, and chlorine has 17 electrons. So we are going to follow our chart up here again. We're going to follow until we fill up to 17, okay? So we're going to use, here I use a different color. We're going to go through the 1s orbital, and we're going to put 2 electrons there. So right here, we're going to label it the line. This is your label for your orbital, like 1s, okay? And then this is your orbital line, and then you draw your electrons in here, okay? So 1s2 is represented right there. So the arrows have to go 1 up and then 1 down. Okay, this is Pauli exclusion principle. Okay, so we have 17 electrons. I just used 2, so we have 15 electrons left. So go back up here to my chart. I've gone through 1s. I need to go through 2s. Okay, so I'm going to label this blank 2s. I'm going to put 1 up, 1 down. So I've used now 2s2. Okay, so I've used 1, 2, 3, 4 electrons. So now I have, I've used 2 more, so I have 13 electrons left. Okay, so next is 2p. So we're going to go down here and label these 3 blanks, 2p, and there's 3 blanks because you can draw p 3 different ways. So when you fill in anything like a p or a d or an f orbital that have more than 1 blank, more than 1 orbital, you're going to take your electrons and spread them out. Okay, this is Hund's rule, that they have to spread out in their orbitals before they can come back and pair up. Okay, and so we used all 6 places of the p orbital. So now we have used 10 total electrons. 2 plus 2 plus 6 is 10. So we have 7 electrons left. So let's go back up here and keep going. So we went through the 2p. Now we're going to go through the 3s. Okay, and so 3s, we can put 2 there. So we put both of those. And now we have 5 electrons left. So we're going to keep going. So we went through the 3s. Next is to go through the 3p. So again, these 3 are 3p. Okay, and we have 5 electrons. So you're going to put the 3 spread out first. So that's 1, 2, 3, 4, 5. Okay, so now all you have to do now is just make sure that you add it up to 17 for chlorine. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So this is your orbital notation for chlorine, okay? So then it just says practice. So I want you to practice these. I'm going to go ahead and write the answers in, and you can practice and then check. Okay, here you go. These are the answers for your practice. Work those, make sure you're doing it right. If you have any questions, email me. Also, there is this instruction on how to use the periodic table. It works pretty easily. So these first 2 rows are S, these 6 are P. Helium actually belongs right here, but that's the only one that's out of place. These 10 orbitals are D, and these 14 are F. Okay, so on the periodic table, it works. So you can go SP, SP, SD, SP, SDP, I'm sorry, I'm probably lost you at this point. But you just read it like you're reading a piece of paper. So the number in front of the S is whatever row number you're on. So this is the first row, so this is 1S, okay? So you read it like hydrogen is 1S1 and helium is 1S2. Okay, that's what their electron configuration would end in. Okay, so again, this is the second row, so this is the second S, 2S. And then after you finish 2S, you follow over to the P section, and the number in front of the P, like this 2 right here, is whatever row you're on. So this one is 2P, this one's 3P because of where it is, it's on the 3rd row. So you read this like you would a piece of paper. So you go through the hydrogen, through the helium. So that's 1S1, 1S2. And then after you finish this line, you're sent to the next one. 2S1, 2S2. Read across. 2P, 1, 2, 3, 4, 5, 6. Read across. 3S1, 3S2. Read. 3P, 1, 2, 3, 4, 5, 6. Then you keep reading. 4S1, 4S2. Now the number in front of the D orbital, you take whatever row you're on and you subtract 1. Okay, so like this is 3D because it's on the 4th row. So 4 minus 1, let me get you a color you can read. So 4 minus 1 gives me 3. So this is 3D, this one section right here. Okay, so if I were reading this and writing this out, I would leave 3P, I would go 4S, 1 and 2, 3D, 1 through 10, 4P, 1 through 6. 5S, 1 and 2, 4D, 1 through 10, 5P, 1 through 6. 6S, 1 and 2. Now right here, you notice this little drop down? This sends you to the F orbitals, okay? And the same way that you had to subtract 1 for the D orbital, you have to subtract 2 for the F orbital. So right here, this cesium to Lu, or not cesium, but Ce to Lu, it belongs right here, which is on row 6. So you're going to say 6 minus 2 equals 4. So this is a 4F orbital. So when you are going through the periodic table, you leave 5P, you go 6S, 1 and 2, and then you drop down and go 4F, 1 through 14, 5D, 1 through 10, 6P, 1 through 6, 7S, 1 and 2, 5F, 1 through 14, 6D, 1 through 10, and 7P, 1 through 6. Okay, so it makes more sense the more you work it, and then there are more instructions right here. This video is getting too long, so I'm going to stop, but just email me if you have a problem.